Okay. Hi, everyone. Apologies for the slight delay. And thanks so much to WebStep and the wonderful IT guys that were able to set up this presentation remotely. I was unfortunately not able to attend in person today, but I'm happy to run you through an introduction to Neo4j and graphs from Stockholm instead. So I hope you're ready for a quick ride. We have 25, 30 minutes here to go. So let's see if we can kick it off. In 2006, an intern at Facebook took about 10% of their data set and visualized it. And what he did was he took the cities that people lived in and how they knew each other and plotted lines between them on a blank canvas, right? So this is all on a completely blank canvas. And what emerged from this visualized data was a map of the world. And you can see borders, you can see coastlines, and it's just an interesting story, I think, of how you can learn something new from data that you already have, right? And if we look at all the big Web 2.0 companies like Google, like Facebook, like Twitter, none of them really thought in terms of graphs, but they all dealt with connections in one way or another. So let's look specifically at Google and web search and the evolution that's happened there. So before Google, the way you found something on the internet was you typically go to a search engine like AltaVista in Sweden, and you'd type in some search terms, and the search engine would go off and look for these terms in the term index, right? And what we'd find was these pages with the same word repeated at the bottom in a 1-point font, right, 1,000 times. And that would boost that page in the overall ranking. And that was obviously completely broken. And along came Google and realized that, hey, there are actually connections here. And if we look at these links that nobody else was really caring about, and we leverage them to signify some kind of importance here, to calculate importance of a page, then we can actually make something really useful. And that's what they did, and Google's obviously been very successful with that in search. And they've taken it a step further as well. So they introduced the knowledge graph, Facebook introduced graph search, adding more facets, right? So it's no longer just a single simple connection. This page refers to this page. But now it's more, if you search for a city, you can get that city, you'll get what country is it in, population, and so on. A lot more data. It's all about the connections, though. So if we go back in time and look at where we thought the graphs would be successful originally, we kind of formulated this matrix, if you will, with 3 industries and 4 use cases. And today, Neo's adoption looks something like this, right? And there are logos that are not on here as well, but you can see that we're heavily used in network data center management, telecommunications, a lot, social, obviously. But there are a lot of segments and use cases that are not on this slide. So where are they? Well, if we add them on, it actually looks more like this. And the main point of this slide is just to point out that graphs are really everywhere. You can look at any given industry, any given vertical, you will find graph data there. You will find connections that are waiting to be leveraged, that are waiting to be used for something, right? And you'll find it within all kinds of use cases as well. And you can add on vertical after vertical after vertical onto this matrix, and you'll find graph use cases everywhere. Right. So let's just get on the same page about what a graph actually is. We haven't talked about that yet. So in a graph database, it's a database product that stores data not as a table, but as a graph. And a graph consists of nodes. The nodes have labels. You can have 0 or more labels. In this case, we have an account node, a customer node, a branch node. It's a way of categorizing nodes, basically. Nodes can have properties. So you have a customer whose name is David, an account with a $100 balance, and so on. And then, of course, we have the relationships that connect everything together. So the customer owns the account, the customer is a customer of a certain branch, and the account was created at a certain branch. You can put any kind of properties on the relationships as well. It's perfectly fine. Same on nodes and relationships. And what we're doing here is we're mixing different kinds of data together, right? We're mixing data about customers, about branches, and it's all tightly coupled together. So what we can do now is we can also introduce new data on the fly. So let's say we want to extend our domain model and add in some employee data. So now we know that Mike manages this particular branch. Well, the second we introduce that data, we can ask a question like, for this manager Mike, give me the branches he manages and the customers that bank at those branches. Then find out if those customers bank at other branches as well, and find me those managers. And maybe those two managers, basically Mike, should go talk to those other managers to get a better picture of that customer, right? That's a query, a question we can ask of that data immediately, and in a relational database, it's like 8 joins to answer that, right? Big difference. If you come from a relational database background, then maybe this example will be helpful. The equivalent example would have customers and accounts, and the way you tie that together is with a join table. And if we remove all the other stuff, we'll find out that the entity tables become the nodes, and the join table entries become the relationships. I hope that's clear. I can't see any nodding heads, but your heads are like a pixel large, so. But I'm just going to assume we're all good. So I'm going to show you a quick demo of the product, just to hopefully clear up some understanding here. So this is a demo of the developer interface of Neo4j, and this is just a small sample data set. I don't know if you can see it, but I'll walk you through it. Here we have a customer who owns a car. The car has had a service event for which we used a certain package, a side impact kit. And the side impact kit contained 2 parts, or included 2 parts that were supplied by a supplier. Right? So if we drag this over like this, we can see the supply chain forming here, right, where you have the customer all the way over to the parts to the supplier. And the kit was installed by a dealer as well. So what we can ask in Neo is we can say, for this given customer, find me what suppliers did my parts come from, right? And that's a question you can answer like that. And it's like 14 joins to get to the other side. In a relational database, and just writing that query would take you half a day, right? And you can turn it around and you can ask, for this supplier, what customers ended up with parts from this supplier? And maybe only the customers where this particular dealer installed the kit. And you also answer that like that, right? And the difference there is you can run that query in a relational database as well, except it takes minutes to run there, or hours. In Neo4j, it takes milliseconds. And the difference between minutes and milliseconds is, well, milliseconds you can actually build a service on that you expose to users that they can consume. You can't do that with minutes. And then lastly, we also do what we call discovery, which is you can pick any 2 nodes, or any set of nodes really, but let's say 2 nodes, this customer, John Doe, and the dealer, Keeley Autos, and you can say, find me a path between these nodes. And the key concept here is the database is fundamentally aware of the concept of a relationship. So the database can follow the relationships for you, right? So you don't, as a user, you don't need to necessarily know what is in between these nodes. It can be a tree sometimes, it's 3 levels deep, or it's 10 levels deep, right? You don't need to know that. The database will follow those for you. So that's just a quick demo of some of Neo4j's capabilities and the developer interface. So let's move on to talking about history. A little history lesson, and we'll talk about the benefits of graphs and why should you use them, right? How are they different from other databases? So how many in the room have heard of NoSQL? Show of hands. can only see the midsection, but I see a lot of hands. Okay, great. So NoSQL, for those of you who don't know, if there's anyone out there, means not only SQL, right? And it's an umbrella term, so it covers a set of databases, and it came about in about 2006 when an emerging set of databases needed to distinguish themselves from the ruling relational database, right? And today, NoSQL as a term doesn't mean a whole lot. If somebody says, I'm running a NoSQL database, you're probably going to ask, what kind of database? No, like, really, tell me, what are you running, right? But it's still very relevant to look at where did NoSQL come from. So NoSQL was largely driven by 4 trends. So let's talk about those trends. Trend number 1 is an increase in the amount of data in the world, right? So if you look at the I don't know which side is which here, but if you look at the left-hand side of the chart, that's basically the 60s, 70s. We didn't have a whole lot of data. 80s, no data. 90s, along came the internet, and we started to produce data, right, to serve to users. And then came Web 2.0 with participation, and people started to produce data on their own, right, pump that into the web. And now we're just on the verge of the beginning of the Internet of Things really taking off, where each little toaster oven produces log data that you somehow want to gain something from, right? The overall premise, by the way, is always that the player who has the most data will win, because you will be able to learn more. That's why everyone wants to hoard data, right? And what we're dealing with here is exponential growth. And there's a story around exponential growth that goes, if you take a drop of water and put it in the middle of a soccer stadium, and it's a magical drop of water, so it doubles in size every minute. Well, how long do you think it takes until the entire playing field is covered with water from this one drop, right? Well, I can't hear any responses now, but I'm just going to tell you it's somewhere below 50 minutes to cover the entire playing field, and it's about 55 minutes to cover the entire stadium to the top, right? And that's exponential growth. It's very unnatural for us to understand and feel, right? And that's what we're dealing with. And basically, it's reasonable to think that whatever technology took us to the middle of this scale is maybe not the only technology that takes us to the other end, right? We may need other technology to augment what we have. Trend number 2 is an increase in the connectedness of data, right? So if we look at an invoicing processing application today and compare it to, let's say, 10 years ago, 10 years ago, we would just care about the amount, perhaps making sure some accounting was okay. Today, we care about much more, right? We care about who is the person connected to this invoice, who's their family, where do they shop, do they have friends, who's an influential friend in their social network that we maybe should market to, right? What are the items in this invoice, and what kind of categories are they in? What kind of category does this buyer fit into? Are there other items that we can recommend that are similar based on what they're buying, and so on? So it just goes out and out and out. We want to know more and more about our data, and this is all about the connections. That's where you can gain the insights. Trend number 3, this is supposed to be a sparse table. Basically, if you take a random person on Facebook, maybe they could have up to 1,000 different attributes potentially, but I think on average they'll have about 10, maybe. And do you want a table with 1,000 columns? Well, probably not, right? In older systems, that's the way we did it. And I've seen software systems with tables that have 300 columns that just have obscure names and mean different things depending on what's in the cells and so on. And it's not a fun experience, and it's probably not what we want for our future projects. Probably want something that handles this in a graceful way. And trend number 4, a change in architecture, right? So it's still the case in many organizations, but we're gradually moving away from using the relational database as the integration hub in our projects, right? It used to be the case, and I very much know it, that you go to the DBA, right? You check out a credential for your new project, and then you use the relational database, and that is what you use for your project. if you want to share data with someone else, then, well, you do that through the database as well. And today we're moving more towards service-oriented architectures. And if you look at, let's say, a retail application again, you might use a specific service for the shopping basket. You might use another service for the product catalog. You might have a service that does recommendations and so on. And what's nice about this is that each service can use a data store that fits its purpose, right? So the shopping basket can use maybe a key value store, who knows? And the product catalog and the recommendation engine can use a graph database because it's suitable for that purpose, and so on. So there are hundreds of databases out there in the database landscape, and if we just look at the NoSQL umbrella as it looks today, again, it is kind of fragmenting today, but we have basically key value stores like React Redis, column-oriented databases, document databases, and then graph databases like Neo4j. And today we talk about graph databases as their own category. They're very much recognized as their own database category. But I think one artifact from NoSQL, being that it was an umbrella term, is that people equated databases with each other. And if there's one thing you can take away, I hope you take a lot of stuff away from this presentation, but if there's one thing, it's that databases are really apples and oranges, right? You cannot always substitute a key value store with a graph database, or vice versa, right? They do very different things, and they have different characteristics. So let's talk about what graphs do well. Graphs are built ground up for storing, or graph databases are built ground up for storing graphs, right? From the storage layer, in Neo4j we have a purpose-built storage layer that works straight against disk or a file system, all the way up to our query language, which is Cypher. It's a declarative query language for graphs. And if you look at the other kinds of databases within NoSQL, like MongoDB, for example, they don't handle connections at all, right? And that's not what they want to do. They want to store individual documents of data. You store a document, and you retrieve that same document. That's what they do, right? They have transactional consistency within the document, but not across documents, and for good reasons. That's not what they're meant for, right? And you might say relational databases, well, they handle relationships at least. Well, sure, but they don't do it very well, right? So anecdotally, if you go back to the 70s, some guy would sit at his computer typing, and his boss would come by and say, hey, I need a report for how many people work in each department, right? And he says, great, I can do that with my join operator and my count function, and produces the report gladly. But today we don't really think of software development in terms as far as data mangling goes, right? We want to think about it in terms of domain modeling. So you have a person, you have an account. I know that the person has an account. Why would you want to use a database that under the hood, every time you ask the question, give me the account, has to go through and match up these numbers, right? And wherever they match, well, that's where the connection actually was, right? And there's a good reason why we still use them, and that's because they're super well understood, right? And they're super mature technologies, and they've been around forever, and everyone knows them from college, right? So there are great reasons for still using them. But for solving that problem of handling our connections, they're actually not the best tool. And then there's the whole schema aspect, of course, which is basically the schema is there to keep things rigid for a reason, and sometimes that's a good reason. But over time, as your development goes on, it goes slower and slower and slower because you have that schema holding you back. And in modern applications, it's usually not preferable. There's also a performance component to this, raw performance, right? If you have a small graph, or if you're just doing one join, you're not going to see a difference between a relational database and a graph database, right? No difference. But once you start adding on joins, once your graph gets bigger, you're going to see a difference. So we frequently work with customers that start out with, let's say, 100,000 users on a relational database, and it works great. And then they grow to 1 million users, and well, it works okay. They add on some caching, as you do, and so on. And then they grow to 10 million, and suddenly their service is no longer real time. right? They can't serve a request they need to serve in real time. And then you're up the creek, right? So what do you do then? Well, you do what everyone does to solve a graph problem in a relational database. It is you denormalize and you pre-compute, right? You pre-compute a specific view to answer a specific question, and you answer it with stale data that you can rush to recompute as often as you can. And that's a deep hole you're digging. And we rescue a lot of customers out of that hole. There's also a readability aspect to it and codability aspect to it. These two queries do roughly the same thing, right? I don't expect you to know Cypher, but if you do, I could put you in front of that Cypher query, and you could tell me what it did in 5 minutes. 5 minutes tops. I don't care how long you've been doing SQL. If I put you in front of that SQL query and ask you what does it do, not kind of what it does, right? Exactly what does this query do? It would probably take you a little while to tell me. Now imagine this is one of, say, 20 queries in your system, on average this size, right? And perhaps the person who's maintaining these queries leaves the company or leaves the group, right? You need to do something with these queries. How do you maintain these? Well, what typically happens is they're thrown out and somebody rewrites it. Either they rewrite new SQL queries, only that time they understand them, or they bring in something else like Neo4j, right? And in this case, for example, if I ask you, well, do this report, but only for the subordinates that work in a department with a budget greater than 1 million, well, your head is going to explode in SQL land. Or you're just going to add it to the backlog of other SQL queries you need to fix, right? So it's a very tangible aspect of working with graphs, working with basically what that means, working with the tool that's right for the problem. We work with the analyst firms as well, talk to a number of them. And Forrester, which is one of the big ones in the US, they estimate that over a quarter of all enterprises in the world will be using graph databases in 2.5 years to support their next generation needs for connected data. And Gartner says that graph databases are the solution that can deliver truly new insights from data. And we are now also on the, they call it the kind of quadrant of operational database management systems, Gartner's quadrant, with Cloudera and others were also added, which is a lot of fun. So let me just talk about a couple case studies, and then we're going to wrap it up. I see I have 5 minutes left here. One is there is a European country on which the entire mail routing system runs on Neo4j. And what they realized was the old system was built on the premise that you ship as many packages from A to B as you do from B to A. And that may have worked a while back, but then along comes, let's say, Amazon and builds a warehouse in location A. Well, suddenly you're shipping a lot of packages into and out of A, and maybe not so much to B, right? And in this picture, you'll see a little gray road that goes across that's effectively not being used as part of the routing, right? All packages go up to the central warehouse and then down again. What they realized was, hey, if we look at our road network, our transport network, logistics, right? It's actually a graph, and we can use an algorithm to find what the most cost-effective way in this graph is. And that's exactly what they did. So today, we route about 5 million packages per day, 3,000 at peak load in Neo4j. They have a team of 50 administrators whose daily job is to keep the graph of connections up to date, right? And it's a truly mission-critical application where when the package slides down the ramp, the barcode gets scanned, computation runs in milliseconds, and then the package goes on to the right ramp or the right truck or whatever it is. And we repeat logistics use cases within many industries, within rail and so on. And it's a very, very graphy area, if you will. I don't know how many of you know Crunchbase. Show of hands. No hands. All right. Well, Crunchbase is a website. It's an online directory for companies, mainly startup companies. It was started in the US. It's part of the TechCrunch network, and it's effectively the de facto source for information on startups. And when they designed their next-gen site, they decided that they needed something flexible under the hood to actually support them in their development, right? So I invite you to go to crunchbase.com and search for any kind of company there, and I think you'll see how it's very graphy data that you're looking at with companies, people that are employed by the company. Company has taken rounds of venture capital from venture capitalists. Draw it on a whiteboard, you'll see it's a graph, and that actually goes in general for all problems. And that's actually, I should mention, it's the first step of getting started with Neo. Go to a whiteboard and just draw your data. That's exactly what it's going to look like in the database. And you can ask anything on it. Two more to go. We work with Cisco. We have several projects with them, but one of them is interesting around support case avoidance. And it's kind of the same as the Google story, actually, not going to flatter them too much, but they realized that they had data lying around that they were not using. And in this case, it was data about the communication between support reps and customers. And a customer may have said, hey, I went to this particular knowledge base article and tried this, and it worked or didn't work. And that link to the knowledge base article can be mined out using text analysis, and then you can create this graph where if you're looking at the knowledge base article at the bottom, they know that there's been a case that mentioned this article, and the case had a solution that referenced another article. Well, it's likely you're going to want to look at that article, the other one, right? It could have what you're looking for. And as you'll see also in these case studies, the red thread, if you will, common theme is that the relational database really hasn't been able to perform for these connections. And as we talked about, the other kinds of NoSQL databases really do not handle connections at all. Last one, native use case from Norway is Telenor. It's been using Neo for quite a while now for their access control system, for their all their business accounts, basically, where they were using a relational database previously, and like I mentioned, you do this thing where you pre-compute stuff, you run around as fast as you can, updating this view, right, that you consume. And updating that view took about, I think, 6 hours a few years ago, and it was expected that this year it would take between 9 and 12 hours to do. And that means that every day your business customers can't sign in until it's updated. And that's not good news for the business in general, right? So now they're running Neo, and it runs in real time. If you want to find out, is this particular administrator allowed to change a particular cell phone plan, that computation runs in real time on the latest data. You don't need to wait for the next refresh. It's always on the latest data, right? Oops. Oh, I added another one in here, sorry. You're going to have to bear through one more. Work with eBay as well. Another great use case, eBay Now. You can order products online, have them delivered to your doorstep. My friend ordered a flat screen TV, and it got to his doorstep in 90 minutes, which is, it's like a pizza almost, right? Which is really cool. And one of their net results that I just want to highlight is 50 times less code, right? Would you rather work with 5,000 lines of code or 100? That's a significant difference. All right. I want to thank you all for coming to listen to the presentation and bearing with us with the remote presentation. Thanks again to the IT staff. You've been amazing. And please reach out if you have any questions. Looking forward to hearing from you. We're doing some training in Malmo as well, if you're interested in learning more about Neo4j hands-on. All right. Thank you.